Welcome to the computer security seminar from Purdue University. Today's speaker is Professor Somesh Jha of the University of Wisconsin. He will speak on retrofitting legacy code for security. Somesh.
Thanks. So the picture on, I'm going to be talking about retrofitting legacy code for security. The picture on the top here is Madison in summer. I decided not to show Madison winter because I think it's not as pretty. I whenever I give a talk somewhere, I sort of kind of remember what are the times I have visited. And this is my fourth time at Purdue. The first time many years back is when I interviewed here. The second time was for a student defense of Jens Paulsberg's, Dennis Brylow. And third was for Midwest Security Workshop. And fourth is to give this talk. So power of 2, 4. So let's go. So here's the thing. So most of us have been taught from the beginning that you want to design security from the bottom up, and in the system design. There are some historical examples of it. So Multics is probably any security class kind of covers that. There are some more recent examples of operating systems and database servers. But you might ask yourself, why doesn't that happen? It's a very good slogan to have. Like we should design from the bottom up, but unfortunately it doesn't happen in real life. And most deployed software is not designed for security. And for example, most of the software is being developed now, very deadline-driven sort of build, design, patch, design, build, patch, whatever. And the second thing that happens is even systems that have very good intentions, like Multics, people have done retrospective studies later on that because of evolving security requirements, your computing infrastructure is not staying static, the requirements that the designers thought about don't apply anymore. Okay, so for example, there was a study by Carger and Shell in 72, many years after Multics, and they showed that there were some mismatches. So here's my rant. This is my only rant slide. That's the soapbox that I'm standing on. A lot of area in software security, at least I have worked in it many years now, and it has a very sort of which is probably very common to security, but still, it's even more in some of these areas in software security, especially malware detection and web security, where it's just like a lot of epsilon deltas in the publication. Somebody has a small technique, somebody breaks it. And after you are, several people get tenure, you write several papers, you kind of notice, okay, where we started here, we haven't made that much progress, okay? That is not so bad. So one thing that is happening now, and these are just few systems, there are some very interesting systems that have come up. So for example, there are operating systems that support very classic ideas like information flow capabilities right at the primitive level in the operating system. So asbestos, high-star flume, it's mostly from Stanford and MIT, and you can, they just have very strong primitives that are being supported there. There is also a lot of action happening at the virtual machine level. So for example, Proxys, what happens is you can, it is a virtual machine infrastructure where you can actually cordon off applications. So for example, your VPN application where you have a lot of sensitive data. You might be able to say that, okay, even if my operating system gets compromised, because I'm running in a different sort of a guest OS, this VPN client, it won't get compromised. So there's some very interesting things happening in the systems literature where at least using this substrate, you can build systems with very strong guarantees. for example, it's not that hard, and it's in their paper as well. By looking at HiStar, you can build a web server so that there's going to be no information flow between connections, the threads that handle different connections. So two different web requests. Okay. Now you might ask yourself, why are these systems not being used? Why? I mean, they lead to very nice OSDI, Usenix security, SOSP, SIGCOMM papers, but why are these not being used? Like, why are you not running it in your laptop? And I have sort of a theory about that. Most, if you just needed an operating system and LS and VI and this, they would be just fine. You need some very complicated applications, like, web server, browsers, and so on to run. So what happens to these applications? Either you develop them from scratch for these operating systems, which is most people, I mean, they have taken years to do that. They're not going to do that. So the basic idea is, what happens to all the legacy code that's running out there? Are you going to re-implement that for everything? Okay, so that's a big barrier to deployment. And so that's what we want to do. We have a very strong foundation in these systems. Can we actually take all the applications that were written for insecure operating systems like Linux or so on and move to these systems? Okay, that's sort of the basic idea. That's why it's called retrofitting legacy code for security. All I have to say is the same techniques that I'm going to be talking about right now are applicable even if you don't have legacy code. So for example, you develop a wiki server, you don't care about like the security that much. Some of these techniques that we're going to talk about can be used to retrofit some of the security code there. Okay, so that's kind of, we want to build that contraption over there. You give us legacy code that is insecure, and we want to provide techniques where we can give you some tools where out comes the secure code. Okay, so that's kind of the holy grail. So there is some already work on it. There is a very nice tool from George Nikula's group at Berkeley called Secured. So what they do is, so initially you can think about this tool as retrofitting C code to do type safety. So what essentially the idea is that you think about in C, you add all eager checks that you want. Like, you say, every time there's a pointer dereference, you add a check saying it isn't a null pointer. Every time there's an array bounds, you check for array bounds. But then this code is going to run 10 times, 30 times, or I don't know how much ever, very slow. So then they use some very sophisticated dependent type system to remove checks that are redundant, that you can statically prove you don't need. Okay? And they're able to get at least, if you believe their PLDI paper, they're able to get pretty good overheads, like 5% or something like that. There's another work from Brumley and Song. What they do is, suppose you have something like SSH server, you don't want to run the whole thing in a privilege mode. You only want to run the component that really needs the privilege in a highly privileged mode. So they have a static analysis technique where they can partition and give you the smallest component that you need to run in that mode. Okay. So there's some other work which I'm not going to talk about. So here are the three problems of this variety that I'm going to talk about, and I might feel free to ask me questions because I'm kind of going to go through all three a little bit quickly. But if you have any questions, please just don't wait till the end. Why did I choose three? It reminds me, Dan Bonet came to Wisconsin to give a distinguished lecture, and he said he was using some assumption, and he called it a classic assumption. I said, why? Somebody asked him, why is it a classic assumption? He said, more than 3 papers use this assumption, so it's classic. So we have greater than equal to 3 problems that using Bonnet's strategy, this is in the similar variety of retrofitting legacy code. So the first thing is, if you are familiar with Linux security modules, what they do is you place hooks in Linux kernel where there is some security-sensitive operation happening, like somebody changing the inode table. And these hooks get called into a policy server. so that you can write your policy and monitor whenever these security sensitive operations are happening. These hooks were generally placed manually, so we will show you how to place those hooks automatically. Okay, so think about this as retrofitting Linux. This is more a retrospective study. We show that the hooks that were placed in the Linux security modules, we could have done automatically using static analysis. The second problem is there's an information flow enabled Java called GIF from Andrew Myers at Cornell. So essentially what it is Java where your type system has been enriched with information flow labels. The problem is that if you take a simple program and you just write labels on it, it's not going to work because most real programs do need to break the type system. So for example, if you just want to take some piece of data which you got in computation, send over the network. Generally, network is the bottom label. It will, it doesn't adhere to the information flow policy. So what you generally do is you put a declassifier there. Think about declassifier as, you're taking some sensitive data and declassifying it to bottom so that it can go over. The programmers have to do this manually, and it's a big issue, right? Once you have real programs, putting these declassified statements is a nightmare. For example, we use GIF in our 642, which is our undergraduate security class, and students had I gave them a small program with the information flow labels and just asked them to put declassify, and they had a lot of trouble. So we'll show you an automatic technique how to place those declassifiers. Okay? It reduces it to a multi-cut problem in graphs. The third problem is Flume. Flume is an information flow enabled system developed by Max Krohn, who was at MIT at that time. So essentially think about it as it's a very system like GIF, which has information flow labels, but now you can enforce them at operating system level. But what happens is, let's say I'm going to take my web server, like Apache, and run it on Flume, then all the label manipulation code that Flume needs, I have to do it sort of manually. Okay? And we will show you how to synthesize the code that is required by Flume automatically using some static analysis techniques. Okay? So what I'll do is I'll move on. We'll discuss problem 1 first. So that we are talking about the same vocabulary. The picture to remember when we talk about Linux security modules is you have a resource user. So in the Linux kernel, it'll be all the processes that call kernel. There's an operation request, which goes to a request manager. So Alice is requesting that she wants to read etc password. There's a reference monitor, which says whether it should be allowed or not. Okay, which consults a security policy to figure out whether Alice should be allowed to read that file, and you get a response. So this is kind of the model that we're going to be working with. So the Linux security modules and SC Linux was essentially trying to retrofit Linux so that it actually, you can enforce mandatory access control, not just discretionary access control. There are other such secure winding systems also developed, for example, TrustedX, X11, Java Virtual Machine, IBM Sphere. But again, the process of putting hooks in this term is that wherever something security sensitive happens, like as it touching an inode table, you want to call into the policy server, insert a hook there, is all done manually. So imagine, I don't know how big the Linux kernel is, but you have to manually look at everything to figure out where should I insert my policy checks to get back. What do you consider security sensitive? So what the basic premise of our work is that program analysis and transformation techniques will offer a principled and automated way to retrofit legacy code with reference monitors. Okay? So the first contribution, which is a contribution in small c, is a new representation of security-sensitive operations. This is, I don't think it's that new, but it was new in that community at that time. This was published in CCS. Then what we want to do is there are two algorithms we use to mine fingerprints, and we'll talk about that more. So I'm just going to kind of run through the first one. So what we did is we used most of our techniques on X server. There's a lot of work going on in communities where they want to secure X server because a lot of the communication there is actually insecure. So for example, what they want to do is people have shown attacks where a remote X server, not X term, not owned by you, can actually snoop on some of the sensitive data. Okay, but in some cases you want to allow this information flow. For example, if there's two sort of X terms that are owned by you, yeah, you want to allow that. So essentially what they want to do is they want, very similar to Linux security modules, wherever security sensitive operations happen, like copy and paste, modification of inputs by other clients, changes to Windows settings, they want to introduce hooks there. Think about hooks as just callbacks, so that you can write security policies to monitor these operations. Okay, and by the way, the style I'm going to follow is on the right are all sort of the references which sort of discuss that. Okay, so this is our same module, just instantiated with the X server. Okay, so in general, here is the kind of the life cycle of how people retrofit these code bases to enforce these policies. Is first you have to go through your source code, and everywhere where there is a possibly a input in sort of a security sensitive operation, you have to insert a callback to the policy server. Okay, but this is all done manually through news groups, forums, and so on. And then essentially what that hook does is calls into a policy server, and then you can decide, should I allow this or not? We are not going to worry about the policy here at all. I'm going to just talk about where to insert the hooks. Okay, this is completely, you can get very sophisticated here, but we are not working on this issue at all. Okay, and this is the poor guy who has to do this all manually. So just to give you an idea that this was not trivial, for X11/SC Linux, it took around 2 years. For Linux security modules, also it took around 2 years. And essentially the way these things happened is somebody said, hey, we should put a hook over there in the Linux kernel. And then somebody flamed him on a forum saying, oh, no, you can't do that. And then, this is how it happened. And surprise, surprise, people found bugs on these hook placements later on. Okay, so for example, Trent Jaeger and his group at IBM, at that time it was IBM, he found there was a violation of complete mediation. So for example, suppose I place a hook somewhere, but the same operation happens along a different path in the program. I should have a hook there as well, right? That's what's called complete mediation. That every security sensitive operation that happens along every path should be mediated, not just one. So they found some bugs like that, which leads me to believe that people are not looking at all code paths. That's essentially what this says. There were some classic time to check to time to use bugs in this placement. So essentially, if you look at this paper trail, essentially it shows you that manually doing these things opens you up for a lot of problems. So our approach is, I hope, principled. What it is we first introduce a language called Fingerprints, which is a new representation for security-sensitive operations, and then we give you an automated way of how these fingerprints can be found through some code mining techniques. Okay, so this is how we'll work. You take your legacy code, in this case X11 server, run it through our miner. You get some fingerprints, which are essentially code signatures for where to put the hooks, and then the matcher looks at these fingerprints and will put the hooks there. And I'll give you an example later. So essentially, fingerprints are code-level signatures of security-sensitive operations. Okay, and I think the best thing is to do is sort of give you just an example. For example, input event code, a security-sensitive operation happens when there is a struct of X event type, and it has a sort of a subfield, and that is whenever this kind of code pattern happens, then we say there is an input event. Okay, so that's precisely an fingerprint. If you are interested in sort of the formal way, essentially think about data log without recursion. They have only ground terms, and here all the terms are over just the security-sensitive resource types. That's all I'm going to. So here's another one. So for example, this one says map security-sensitive operation happens when that field is set to true, and that type is set to map notify. If this code pattern happens in the code, then we say the map happens. Same thing with enumerate and so on. So once you do that, you can see what you can do now is, if you just are a GCC hacker, you can look at these code patterns, walk over the AST representation of this in the compiler, and whenever you see that pattern, you place a hook. Right here. Here. So it performs enumerate, and then that means you put a hook. Okay? So essentially the first thing we showed is that just by looking at specifications of these security-sensitive operations, the operation of placing these hooks becomes automated. So at least you won't have the time, sort of the complete mediation problems, because if your compiler. So at least the first kind of problem where you missed some cuts won't happen. Okay, but again, the same thing. Somebody still has to write these specifications of security-sensitive operations. Now, the idea of this is not new. If you look at any software model checker, like Dawson-Engler's metacompilation or Chen and Wagner's MOPS, they use these kind of code patterns to define atomic properties. So for example, they want to find out where does a lock happen, right? Because they don't want double lock. So they will write these code patterns for locks, and that's where we mostly got the idea from. And essentially what happens there is that anytime there is this pattern, then they say, okay, somebody's trying to acquire the lock. We tried to get very sophisticated, but it was not needed for this problem. This was kind of the minimalist formalism. Madison is the town of Frank Lloyd Wright, so we go for minimalist architectures. It's the minimalist pattern language we could come up with, which was still good. Now, if you're a software engineering person, this is very much, if you're into aspect weaving of Gregor Gonzalez, you can think about this as weaving security aspects in. If that's and I had given a talk at UBC, and he obviously really appreciated that. Now the whole idea is that somebody still has to write these specifications of security-sensitive operations. We want to get rid of that as well. So what I want to give is, I want to give you a dynamic fingerprinting technique, and then there is a static fingerprinting technique which was in ICSI, which I won't be able to get into. Okay, so here's what we want to do. You give us the source code and some very high-level specification of input event, create, destroy, and so on, and out come these fingerprints. Okay, and here's and so for example, the kind of things that we need is something like this: that input event is input some sort of a description of it, and I think the best thing is to just give an example here. 1 second. Here. So all we are using is, you need a specification something like this. You need to say that whenever I open an X term, then create and map security-sensitive operations happen. Okay, so this is given by an expert of X server. Whenever I close an S term, there's a destroy and unmap, and so on. Now let's say I run my X server and open an X term and just collect my trace. I know that the fingerprint of create and map are in there, right? Because I know those operations happen. but I only want for create. I don't want the map guy to pollute my trace, right? So what can I do? So if I now intersect these two traces, think about those as sets and you are intersecting them, then this guy is still in there, but if I subtract x, the trace for x term for it, then the only thing left should be create. So think about this as a set. Create map, you union with this, subtract this. The only singleton set should be left is create. So if I take the trace corresponding to opening an X term, intersect it with the trace corresponding to open browser, and subtract it with the trace corresponding to move X term, I will get essentially a localized trace for create. Okay, it doesn't quite work like that. I mean, there's some, but this is sort of the basic idea. So it is all based on forming these set equations. Think about this as a hitting set. So essentially what you have is you're creating a set equation that leads to a singleton set, create. And all those equations that in this are the trace operations you do. Okay, and this was actually remarkably useful. And obviously this is, it's NP complete to get the minimal equation and so on, but these operations are so few that we were just able to just do it exhaustively to find these equations. I am sort of not going to go into the experimental methodology. We use GCC. Essentially what happened is from millions of events that you have to see, you can localize that. For example, for create, we were only able to look at, you only had to look at 126 statements to figure out what the fingerprint was. Okay, how much time? Okay, so as we know, all dynamic techniques have this problem. There's a false negative problem. If you haven't seen a path before, you're not going to exercise it. Remember, there's also a high-level description needed, that table that I talked about. And the operations have to be manually induced in the server. We fixed that, and we had a static fingerprint mining technique that was in XC07, which I'm not going to talk about. I'm now going to move to problem 2 of putting mediation statements in Java. This appeared in ESOP 2010. This was a collaboration from Penn State. These 3 guys are at Penn State. I'm at University of Wisconsin, and these 2 guys are at UC Berkeley. This guy is not my cousin. It's just they're like a lot of people from this region have the same names. Okay, so the idea is that here's a simple code which essentially takes 2 passwords from the user and checks whether they're the same, and then writes to a file. And obviously you don't want to write to a file plain text, so you would encrypt it. So this is, to me, this is a prototypical example of a mediation. You're encrypting so the data is okay to release. That's declassification. In literature, Trent is much more example. There are many kinds of mediation statements. Declassifiers ensure that secret data is encrypted before it's released, just like what I just showed you. Endorsers ensure that low integrity data is sanitized before it's used. So for example, if your data is coming from a network and so on. So the whole idea is that you want to do this automatically, place these mediators automatically. Okay? Let's talk about that. Is everybody familiar with GIF or not? You're? Okay, so think about Java. Just, it's pure Java, but you are enhancing the type system by having information flow labels. Okay, and that type system is carried through in Java. So, it's I think Andrew Myers has been working on it for I don't know how many years. But what happens is, as I told you, if you take a banking application, right? And you just do this information flow labeling like Andrew does, it will not work. You have to put these declassifying statements, because for any real program, you have to violate some of this type system. For example, think about taking your account and sending it to you, even if it's encrypted, that's violating the type system. So, but you can put a declassifier there saying, I know this is encrypted, so you're okay. Okay. So, just to show you that this is not easy, we had an FSC paper where essentially we looked at some of this type system, and we found out that for very simple programs like mental poker, Java purse, and so on, if you didn't put declassify statements, there were a lot of places, there was a lot of choice of putting these declassify statements in. So just kind of this study showed that it isn't trivial. There isn't like, for example, let's say I have a banking app. If there was one place where I could put the declassifier and it all worked, then you can sort of say that why the heck do you need a tool? I can find that by sort of inspecting. So essentially this study says there is enough complexity in these information flows that you can't reason about this just by staring at the code. Okay? And essentially, if you think about it, what the mediation statement does is it is resolving the security exceptions that are created by the information flow type system. Right? For example, if you send a data out and the network is bottom and the data is high security, that's a security exception. And by encrypting it and then sending it, you're actually just mediating that security exception. So this was the big sort of aha moment for me, that essentially what these declassified statements are doing is like exception handling for information flow type system. Wherever the type system says there's something wrong happening here, I need to put a declassified statement and mediator to sort of resolve that security exception. To me, that was like kind of the aha moment. Another aha moment came from a paper by McCamant and Michael Ernst from PLDI 2008, where essentially what they were looking at is not information flow. They wanted to find out, let's say I have like a password checker or something. How much information does it really leak about my password? Okay, so they were interested in a pure measurement study. This is something that we were, for example, talking about this morning. So, for example, you have some sort of a web server. It does some cookies and so on. You want to find out, okay, how much really it is in private information is it leaking? So they had a very interesting idea. What they did is that you can imagine all the information flowing in your system as a graph, and the min cut on that graph gives you a nice version of how much information is it sort of leaking. And I'll get a little bit more into that. That was kind of another aha moment that we can use something like that. So let me sort of give a small example. This is an example called log rotate, which a lot of people from the information flow community use. And essentially think about these as dependency edges. Okay? That actually this is a little bit. So for example, this depends, dispose file, this file name depends on new log file. Just think about these as program dependence, that variable depends on that. Okay. So now what we do is, does everybody know SSA form? What SSA form means? So essentially what happens is, these are called single static assignment forms. Imagine all of them has been converted to SSA form. Okay. And each kind of line here in this graph is that there is an information flow or a dependence from that entity to that entity. So think about, what is that? Rotate count 6 to I, which corresponds to probably that one, or this one. This one probably, rotate count I, from this for loop. So think about this as there is a flow of information from here to here. This is your this is your high security variable config file, and this is the log file that you're writing to, and these are all paths through which the information can flow. So, for example, new name 9 depends on new name 99. I mean, so essentially think about SSA form here as each time there's a variable on the left side, I just rename it. Okay, in this case that works. So this is your high variable config, and this is your log. And if you want to and each path here shows you a flow of information. So you can each will correspond to a code path which allows a flow of information from config to logbl. So intuitively, if you view it as a graph, what do I want to do? Where do each of these correspond to a statement? Where do I place my mediation statements? Because I don't want any flow of information here. It's a directed graph. I don't want any flow of information. If I can get a vertex cut here so that every path from here to here is disjoint, and I place my mediation statements there, I'm done. Right? And that's exactly what happens. So that is another cut. Okay? Now notice that min cut you can do in poly time if you just have high and low. But real security lattices you just don't have high low, you have multiple sort of lattice levels. So you have to generalize this problem. Min cut is not enough. So in general, general lattice has more than 2 elements. So you have to look for a min cut that separates pairs of elements in the lattice such that L1 is not less than L2. In case of high and low, it was just that high and low, but in general lattice, you essentially have to kind of separate out any incomparable things in the lattice. Okay? So, but the basic idea is the same. Here there were like 2 things that you want to separate. In a general lattice, there will be more than 2 things you want to separate. Fortunately, there is a generalization of min cut, which is called multi-cut, where essentially you give a pair of vertices in a directed graph, and you need to find a minimum number of vertices that separates every pair of vertex in that graph. And that fits very nicely. That's exactly what we have. Our algorithm is based on an algorithm by Kachayan from that 2007. And actually, in general, the problem is hard, but at least we didn't encounter it too much in practice. If you're interested, there's a very nice paper by Chuzoy and Khanna on sort of characterizing these multi-cut problems. Okay, and that's essentially what we used in that. So the kind of the aha moment of this ESOP paper was that we reduced the problem of placing mediators or declassifiers to problem of finding multi-cuts in these information flow graphs. Okay, so that's kind of the aha moment. So, okay, yeah.
Is the problem not hard in practice?
Oh, yeah.
Is the problem not hard in practice because the number of security labels is low, or because these graphs don't grow very large?
So I think the problem is hard if you're looking for minimum number of vertices to cut the graph. But what happens in real programs, you want small enough mediation statements to put in. Even if they are not minimum, it's okay. So we are not looking for absolute minimum as long as the number doesn't get out of hand. Does that make sense? So for example, in this case, 3 is the minimum, but even if you put 4, for a program, that's not a big deal. So though I think it becomes easy, not because of the structure of the graph that much, just because we are not looking for absolute minimum.
But since you mentioned that one of the examples was declassifiers, if you have too many of them, wouldn't that mean that you're encrypting more than maybe you need to, so the performance will suffer?
Yeah, but I think what we found in our applications is that it's a little bit more, but not too much. You still get a lot of benefit from that. But I think that's a good point. Now, one thing that is missing from this, which is very good for sort of, and I'll kind of talk about it at the end, but I just wanted to get to the sort of the third one. So the problem 3, this is a problem which has a Purdue connection. This is the 2 co-authors and sort of collaborators in this are Tom Reps, who doesn't have a Purdue connection, but there's another guy, Bill Harris, who was an undergrad here and is one of the star students in our department now. So he's publishing top papers every year, so you guys trained him well, and we are taking the fruits, so to speak. This is being led by Bill Harris. And here the idea is that you are given a program like Apache with no information flow stuff in it, okay? And you have a diffc enabled operating system like Flume. Diffc is discrete information flow control enabled operating system. Think the ideas of GIF, but carried over to operating system. And what you want is, what we have is that we have a system called Apache, which gives you output as Apache plus all the diffc code that you need to run on Flume. Okay? And essentially, this is a slide that Tom Reps actually came up with, and I really like it. Essentially, the whole idea is that without our tool, there is a semantic gap that exists when you're writing secure applications. So your security policy that you had in mind, that some high-level one, that's kind of spread across the code. There is no declarative representation of that. I mean, you don't want a security guy to think about, oh, what is your security policy? Well, look at my Apache code for Flume. I mean, that's not, I mean, and that's what we want to avoid. That you should not have to look at the code to get a security policy. You should look at some declarative file or something which says that, and the code should be sort of sprung in automatically. Okay, so that's essentially what this guy is saying. Okay. So that's what we do. We call this project called Policy Weaving, and it has now dollars behind it. We just got funded by the DARPA Crash program. And essentially the whole idea here is that you give us the system, like Flume, some semantics of what it means to manipulate label code in Flume. You give us some the code that you want to instrument, and you give us the security policy, and all the code that Flume needs we synthesize automatically. Okay, and that's what this is. Bill Harris came up with this acronym called SWIM, Secure What I Mean, and we had a paper in CCS 10 there. So I'm not going to. I'm going to just jump into the example. Why is it not? Okay, so here's how it works. I hate animations. Okay, so here's the top level is your web server. With sort of a caricature of that. Think about Apache. This is a requester. These are worker threads that are spawned when you want to have new connections. Okay, and that's kind of the code of the insecure program showing on the left. And your security policy might say that, hey, workers cannot talk to the network. Okay, cannot send information over the network. It has to go through some special proxy. Same thing with the requester, but the requester actually can spawn some processes. Okay, and then we have something called the C-Flume Policy Weaver. And all the label manipulation code that Flume needs comes automatically. Okay, and the magic here is that we have a constraint system that essentially represents all the Flume semantics, what it means to manipulate labels, all your policies, and all constraints that we get from program, and feeds it to SMT solver, and the solution actually corresponds to synthesizing the code. If the SMT solvers were not fast, we'll be dead. Okay, so we are actually jumping on the bandwagon of SMT bandwagon, and actually, again, I think you don't do research in vacuum. There is a paper by Sumit Gulwani and Jeff Foster and Srivastava in Popple 2010, where they used SMT solver actually to synthesize programs, complete programs. So think about what it happens is, you give me a skeleton of a sorting program, and you leave some holes on how you manipulate elements. And they could actually use SMT solvers to fill those holes automatically. So they were able to kind of synthesize quick sort and heap sort. You don't want to tell that to the undergrad students here because there's no homework left to do. But the problem is they couldn't scale up to large programs. Remember, our problem is slightly simpler. We are not trying to synthesize Apache. All we are trying to do is Apache is given. We are trying to synthesize the shimmy of code that it needs to run on top of something like Flow. Okay, so that's why our job is much simpler. But the motivation came from Popple 2010, and there is a very related paper by Eddie Kohler and the name that I won't pronounce in Eurosys 2008, which essentially tries to enforce our main story. I mean, they kind of did the marketing for us. Essentially, they say that, hey, this whole idea of having a security policy in this code that you have this label is a bad idea. You should have some sort of a declarative language, and then use that declarative language to actually write this code. But they didn't have the tool to actually synthesize this code automatically. And the key piece was the SMT solvers. Okay. Now, one thing that really surprised the heck out of me, if you haven't used SMT solvers, you should. We had like close to 15,000 variables and like maybe 300,000 constraints. And I was really worried because I said, this thing is it was able to chew it up in minutes, this SMT solver that we had. So the whole idea is that the kind of SAT problems that you are generating here is not like factoring prime composite number. It's some very kind of a easy problem. Okay, so based on that, and I have 3 minutes 22 seconds left. So if things are still bothering you about the talk, please ask questions.
Are there any questions?
Nick.
Regarding the use of the SMT solver, have you found some connection between the expressiveness of your declarative security policy language and the type of constraints or the hardness of the problem that is generated?
So I didn't get into the detail. The constraint system in general is NP complete. So you need full power. The constraint system that we use is NP complete. So you need the full power of the SAT solver. Now, what happens is that, is there anybody familiar with the small model theorem, small model theorems in logic? So what happens in logic is, suppose you have a logical system. A logic has a small model property. If you give me something and say, is it satisfiable? I can't tell you that, but I can bound the model size, saying if this thing is satisfiable, then it has a model up to a certain size, given the size of the formula. So if your formula has size 10, then I can tell you that, hey, in this polynomial in 10, your model will be there. So what happens is that in SAT solvers, those are very useful because that tells you exactly how many Boolean variables you need to encode them. So our constraint system is NP complete, but it has the small model theorem. So we can get away with encoding very small variables. But yeah, it is fully as expressive. So it's NP complete, so it's as expressive as full SAT. Question? 1 minute 33 seconds.
I have
Yep.
a question and this is on here. Is there any hope of doing the retrofitting at the machine code level rather than the source code level?
So we haven't pursued that. The problem is the kind of sophisticated analysis we need. We need sort of all points to all the structure information is sort of not available at the machine code level. But I know that Tom and one of his students, Tom Reps, are looking at whether some of these ideas can be applied to machine code. But my view is that at least at this point, we need rich enough information that I think at least I'm going to stick to source code for now. But it is, if you give me enough sophisticated static analysis for machine code, then yes, I can probably carry some of the ideas there.
Any questions? Well, then let us thank our speaker.
Thanks for inviting me.